Okay, the twin paradox now part 4. I want to do a brief review of where we've been with this. And also, as you can see, we're going to do something with the Lorentz transformation here. If this is going to distract you, I'd suggest pause the video right now, write that down, and then so you can focus on other things we're going to be talking about here, and we'll get to this in a few minutes. But remember, here's the situation in a smaller diagram this time. We had Alice in the rocket going at 0.6 C, gamma factor of 1.25, Bob in the lab frame. And this time we're going to specifically talk about the rocket and lab frame. And as you can see again over the equations here, we've got R and L standing for rocket and lab. Not right and left, but rocket and lab, just to try to keep things straight here, because sometimes we've had Alice moving and sometimes we've had Bob moving in previous analyses and examples. And so sometimes if we just keep using A and B, Alice and Bob, then we forget who's moving and who isn't. It gets even more confusing perhaps. So Alice is moving this time in the rocket frame. We measure things in light years, and went out to a star 3 light years away and then traveled back again. So here's what Alice's world line looks like in Bob's frame of reference. So out to 3 light years and then back. So back in the negative direction, leftward direction, and ends up, according to Bob, 10 years later. He observes her, takes 5 years to get to the star. 5 years times 0.6 times the speed of light is 3 light years, and then another 5 years back. So his analysis, remember, was fairly straightforward. He expects he'll see 10 years tick off on his clock, and because of time dilation, the factor, the 1.25, 1 over gamma factor, he sees Alice's clocks tick off 4 years in each case. And then we did the analysis, so that was Bob's analysis via time dilation. We did Alice's analysis where she sees Bob essentially going away and the star coming toward her and then back again. And for that it was a little more complicated. We had to use not only time dilation but length contraction, because she sees the distance to the star not as 3 light years as Bob does, but a contracted distance. So we had to take that into account. And once we did that, we got the correct number of years ticking off on her clock, 4 years. And then, though, the real puzzle was, we also saw that Alice, of course, saw Bob's clocks running more slowly. And the number we got for that was 3.2 years, again, the gamma factor. 4 years on Alice's clocks. She sees Bob's clocks ticking more slowly compared to her lattice of clocks she compared it to, by a factor of 1.25, which would leave 3.2 years. So why doesn't Alice see Bob only age 6.4 years? And remember, the key was that when we analyze the turnaround here, essentially Alice is changing frames of reference. And so her lines of simultaneity were parallel to the green dashed line that slopes down like this. And when she changes frames of reference, then her lines of simultaneity are parallel this way. And at that turnaround, there's a jump that takes place between frames of reference, and therefore Bob's clocks speed up compared to Alice's clocks at that point and tick faster, as it were. You can actually delve into the details of that turnaround and analyze it and show in more detail, if you want, that actually occurs. But for our purposes, we just say, hey, change it in frame of reference. Therefore, we can see on our diagrams that we did that we get this jump in time from 3.2 years up to 6.8 years. And then during the second leg of the trip, again, Bob's clocks, as far as Alice observes, tick off 3.2 years. Add it all together and you get 10 years. So both of them come up with the same answers, although by different reasoning with that. Another thing just to mention here, and that is because some of you are probably still thinking, well, it just seems that aren't they symmetrical? In other words, Bob watches Alice go away and come back in. Alice in her spaceship, from her frame of reference, watches Bob go that way, the star come this way, and then back again. Just think about it. It seems very symmetrical, but we made the point that only Alice has the acceleration involved. And Bob actually does not feel any acceleration. We mentioned, of course, like if you're in a car that's accelerating, you can feel it being pushed back in the seat or decelerating, you're thrown forward a little bit, or even moving side to side around a curve. Another, maybe more physics way of doing that is to do a simple experiment. Drop a ball And if you're moving at constant velocity motion, and there's no wind or anything like that, if you drop a ball, it will drop right down at your feet. Because the ball participates, again, we're talking about slower speeds here. We obviously did the analysis with relativistic speeds, but the ball participates in the motion of the object as you're moving. If you're accelerating, however, what happens is the ball falls behind you for a large enough acceleration. For a smaller acceleration, it actually does, but you just can't notice it as much. And so essentially what happens is as you drop it, the ball has the velocity at that point, so it will be going forward with you, but you sort of accelerate it out from underneath it, and therefore it falls behind you. Or if you decelerate, it falls ahead of you because it still has that initial velocity. You've slowed down now, and so it moves ahead of you. So Bob could do that dropping ball experiment all he wants, and during this whole time, it would just fall at his feet. He would not undergo acceleration, whereas Alice would when she was at the turnaround point, decelerating and accelerating. So if that helps a little bit to see what's going on, that even though it seems symmetrical, it actually is not. And of course, the acceleration or deceleration, acceleration at the turnaround point is the key factor because that's what changes the frames of reference for Alice. And then you get the jump going on there, the jump in time as Alice observes Bob's clock. So in one sense, we've talked about how special theory of relativity is all about inertial frames of reference, only applies to that, not in cases of acceleration and deceleration. But you really don't need, say, the general theory of relativity here, which deals with acceleration and deceleration, because you just assume the acceleration and deceleration occurs over a short enough time that you can essentially analyze it using the special theory. And it's really the change in reference frame, which is covered by the special theory, that gives us the results here. So yes, acceleration, deceleration is involved, but we can analyze the results and get the correct results using the special theory. So all that being said, what about the Lorentz transformation here? What we want to show is that you can get the same numbers using the Lorentz transformation, perhaps a little faster as well. The downside is, first of all, you've got to use the correct formulas, of course, the correct versions of the formulas, so you've got to be careful about that. But the downside is you don't get as much feel for what's going on as you do when you break it down via time dilation, length contraction, and leading clock's lag, the relativity of simultaneity. But do want to show that you can do this. Again, our basic equation that we suggested you memorize, if you're in the mood for that and want to use this a lot, is this one here, where we have the rocket moving away in a positive x direction, L for lab. And one way to memorize remember whether it's a plus or minus here is just think about, okay, the rocket's moving away from me if I'm in the lab. That means any rocket value for x will be a bigger value for me because it's moved away. And so if they measure something 10 meters ahead of them, that's going to be maybe 30 meters for me if they've moved 20 meters in that time. So if you can remember that basic situation, rocket moving away, it's going to be a plus sign here in the basic forms of the equation. Then from that, you can derive pretty easily just in your head that the other forms of the equation here. So let's start, though, over here with A, calculating Alice's results using Bob's values. And so Bob's values are the lab frame values. And to Alice here, Bob is moving in the negative x direction to the left. And that's why we've got minus signs in these versions. But otherwise, Bob's values, the reason it's nice to start off with that, is Bob's values are pretty obvious what's going on here. So on the outbound trip, Bob's value right here is x. We'll just put this in. So we'll say xl equals 3 light years, right there. And then the time is 5 years. TL equals 5 years. And so that's for the outbound trip. So the question is, okay, those are Bob's measurements right there. What are the measurements x and t for Alice in the rocket at that point? And if you plug the numbers in here, gamma is 1.25, plug these values in for xl and tl. V is 0.6 c. We're using c equals 1 because we're doing light years per year for c. Plug that all in, and you'll find you get 0 for here, and you get 4 for that. And think a minute, does that make sense? Well, yes, because this is Alice's world line, right? She, in her frame of reference, hasn't moved. She's at 0 in her frame of reference. And her clocks tick off 4 years, and that's what we got before. So yes, that does make sense there. Now we'll get to the inbound trip in a minute. That's a little trickier. Let's do the outbound trip for Bob's results using Alice's values. Okay, well, we could either do Alice's analysis as we did with the length contraction time dilation, or even just use these results here. We know that Alice here is going to be XR at the turnaround point there, at the planet or star. XR equals 0, TR equals 4. And you plug those values in, and you get, as you should, 3 and 5. In other words, Bob's measurement of that space-time point is XL equals 3, XL equals 3 light years, and time 5 years there. So that checks out, as it should. Now what about the inbound trip here? We have to be a little careful here because these Lorentz transformation equations apply when the origin is the same for both of them. In other words, when we're starting things at the origin, and at that point Bob's clocks and measurements are at 0, and same thing for Alice's, then these equations apply. In this case, we're out here. Our starting point is out here at the point 3, 5, and we're going back to the left. So what we have to do to make it easy to use our general equations here is to redefine this as the origin point. And then what happens here is, if you think about it, if this now is our new 0, 0 point, just for the second leg, the inbound leg analysis right there, that means, if we think about it, XL is going to be negative 3. Okay, so this is now 0, count off negative 3 back to here, and so we can write XL equals negative 3 in there, and TL is the same. TL still goes 5, up 5. So it's really negative 3 TL equals 5 years. And if you plug in those values, negative 3 and TL equals 5, just from the diagram here, again, you're going to get XR equals 0 and TR equals 4, another 4 years, as you would expect. So 8 years there. And same thing, inbound trip over here, although in this case we just use XR, again, XR equals 0 and TR equals 4. We've redefined the origin to be 0. So, and again, on the rocket ship for Alice, she's just at 0. She hasn't moved as far as she's concerned. And TR equals 4. And you plug those in. And notice what happens here for this one. Actually, you get XL equals negative 3. Okay? And TL equals 5 again. And so you say, well, wait a minute, XL equals negative 3. Well, remember, again, we've defined this as the origin. So really, as far as Bob is concerned, Alice has moved negative 3 in the negative direction, in the left direction. Okay, and once again, L and R here are not left and right. They stand for lab and rocket. So it just shows us, yes, we can get the same answers using the Lorentz transformation as long as we're careful with our plus and minus signs and think about the origin for the inbound leg there. Let's also, one other way we could do this, just to review a number of things we've done in the past and used for calculations, and that is the invariant interval. So let's just quickly put that up here and see how that works and get the same results, or we should. Okay, so remember the basic form of our invariant interval equation between two space-time points essentially is c squared delta t, and here, well, again, we'll use lab and rocket frame again, so L and R. So we'll just do L squared minus, let's use delta x, just to remind ourselves it's a difference in coordinates, delta xl squared equals c squared delta tr squared minus delta x r squared. And again, what's nice, if we're using everything in light years per year, light seconds per second, then c just becomes 1. So we don't have to worry about the c's there, and we're just looking at the difference in the time coordinates. And so for the outbound trip, outbound, For the outbound trip, we have delta XL is 3. Okay, so let's write that down. Delta XL. In other words, it goes to 3 minus 0. So difference is 3 light years. In this case, delta TL, again, we're assuming we've done Bob's analysis. Delta TL is 5 years for the outbound case. And the other nice thing about sometimes with the invariant interval, if we're doing delta XR for Alice, as we've already mentioned a couple times, that's just 0. Right? Because she stays, from her frame of reference, she's not moving. She's just in her spaceship. And so we can see we have everything we need here. Except, so we've got delta XL and delta T sub L. We have delta XR over here, which is 0, so that disappears. And so we're just left with delta R. And when you do that, plug in the numbers here, we get delta T sub R equals 4. It's easy to verify that if you want. So that's the outbound trip. For the inbound trip, very similar again. So again, you can see here, it's an even easier calculation than the Lorentz transformation if you know the values, and depending on what the situation is, sometimes it's very easy to see what those are. But you lose the insight behind it, and that's why we started off using, first we did our diagrams, the space-time diagrams, and then did our analysis with time dilation and so on and so forth. Now for the inbound, notice what happens here is, as far as Bob is concerned, Alice ends up at 0 and starts at 3. So in this case, delta XL is negative 3. You do the second point minus the first point. 0 minus 3 is negative 3 there. Delta TL, though, equals 5 again. Delta XR is 0 again. And once again, you get really the same thing. You get delta TR equals 4 when you work that out. So that's the invariant interval approach to this. Again, it can be useful in certain cases just to get a quick answer if you need it. One final point here to make or remark, and that is we've mentioned a couple times about experimental results that confirm all this, because no matter how many thought experiments we do like this, there's always the lingering doubt that, is this really real? Does it happen this way? It seems logical once you, starting from Einstein's principles and sort of building on those, and yes, we can see how with the light clock we get time dilation, lengthening traction, relativity, simultaneity, but because it's so far out of our everyday experience, it's sometimes just hard to know. So I've mentioned, for example, the muon experiment. They've also done experiments with muons in particle accelerators, where they essentially have some muons just at rest, and then other muons circling around them. And from those, they can show that the particles at rest will decay faster than those in motion. So again, it shows the clocks slow down for the ones in motion. So that's well understood and demonstrated. But I've also mentioned these airline experiments they've done. The first one, just if you're interested a little bit in this, is done in 1971, I believe, where they had 2 accurate atomic clocks on the ground, and then they took some portable ones up in commercial airliners, actually, and flew around. And some flew eastbound, some flew westbound, and they had to take into account a number of things going on, including the rotation of the Earth and the fact that clocks actually run faster at higher altitudes than lower altitudes in a gravitational field like the Earth. In fact, next week we'll talk just a little bit about that to see how time dilation occurs in a gravitational field. So they had to take those things into account, as well as the velocity of the airplanes. And the eastbound and westbound was a little different because Earth was moving, and therefore the clocks on the ground were not completely stationary, but they were moving on the Earth, and so on and so forth with that. So what did they find? Won't give you all the numbers here, but to give you an idea, for the westbound clocks that went on the planes, they had a prediction of that the difference between the clocks and The stationary clocks, stationary in the sense they were still on the ground, was 275 plus or minus 21 nanoseconds. That was the prediction. The result was 273 plus or minus, I think it was about 7 nanoseconds, something like that. So pretty close. The eastbound result wasn't quite as good as that, but this was, they predicted the clocks that flew around would run more slowly than the clocks on the ground by this amount, and the experimental result was very close to it. They actually repeated this in 1996, a form of this experiment where they had, by that time they had better atomic clocks, about 25 years later, and they took one on a jetliner from Washington, D.C. to London and back again, and the prediction there for the result was about 30, almost 40 nanoseconds, I think 39.8 nanoseconds, and the result was about, I think, 39 plus or minus 2 nanoseconds. You don't have to remember these numbers, of course, but the point is they're getting results that are very close to the experimental or the theoretical predictions, and also just the fact that these are very, very small time amounts here. Billionths of a second are what nanoseconds are. They've also done, in the intervening years, since 1996, not that long ago actually, but there's an experiment done in 2010 at the National Institute of Standards and Technology, NIST, which is in Boulder, Colorado in the United States. Other countries have these things, have these institutes as well that are in charge of standards and making very precise measurements and things like that. So in the United States, it's the National Institute of Standards and Technology. It used to be the National Bureau of Standards, but they changed the name a while back. Anyway, 2010, they did an experiment with a very, very accurate form of clock that they had developed. And instead of taking on a jet airline or anything, they could just do it within the lab at various speeds, even as low as 4 meters per second. Okay, so that's about 12 feet per second, if you want to think in those terms, up to maybe about 90 miles an hour. So they did a variety of speeds, but slow speeds. We're not talking about jetliner speeds. And the experimental results matched up nearly perfectly within the very small error bars they had to the predictions of the special theory of relativity. So the theory of relativity is well understood theoretically. It's well supported experimentally. Doesn't mean that it's possible we could discover something that meant we had to change a little bit. Maybe the speed of light isn't constant over the time of the universe or things like that. And every once in a while in the news you'll hear something about some experiment that says, maybe something travels faster than the speed of light. These experiments are so subtle, though, that often there are confounding factors that you have to take care of and take into account. And it's very difficult at the precision involved to really see if something is going on or not. And so far, every time, Einstein, in a sense, the theory has been proven correct. Okay, so that's the twin paradox, most famous paradox of all, and just some of the analyses we've done in various ways with it, and then just the experimental results that show, yes, no matter how weird it seems, the twin paradox actually is an experimentally proven fact.